The Explorer mission is arguably one of the most remarkable and enduring achievements in space exploration. Originally designed as a short mission to investigate the outer planets of our solar system, Explorer has far surpassed its initial objectives, evolving into an expedition that has provided invaluable data about the universe. This incredible mission, now ongoing for over 40 years, continues to relay significant information back to Earth, revealing discoveries that could challenge our current understanding of physics. Recently, Explorer 1, the most distant human-made object, continued sending usable data after years of sporadic transmissions. Join us as we delve into Explorer's extraordinary journey and its surprising findings. The Explorer saga began in the mid-1970s when NASA identified a unique planetary alignment that allowed a spacecraft to visit all four gas giants, Jupiter, Saturn, Uranus, and Neptune, in a single mission. This alignment, which occurs once every 176 years, enabled the spacecraft to use the gravity of each planet to propel itself to the next, significantly reducing the time required to explore these distant worlds. NASA's Jet Propulsion Laboratory, JPL, designed two spacecraft, Explorer 1 and Explorer 2, to take advantage of this rare opportunity. Both spacecraft were equipped with scientific instruments to study the atmospheres, moons, and magnetic fields of the outer planets. Launched just weeks apart, Explorer 2 on August 20, 1977, and Explorer 1 on September 5, 1977, these twin spacecraft embarked on carefully plotted courses. Explorer 1, the faster of the two, was directed toward Jupiter and made its closest approach in March 1979, capturing stunning images of the planet's dynamic atmosphere, the Great Red Spot, and its moons, including the volcanic Io and icy Europa. These observations transformed our understanding of these celestial bodies, revealing active volcanoes on Io and the potential for a subsurface ocean on Europa. After its successful flyby of Jupiter, Explorer 1 continued on to Saturn, arriving in November 1980. It provided the first detailed images of Saturn's intricate ring system and discovered Titan's thick atmosphere, rich in nitrogen and methane, sparking interest in its similarity to early Earth's chemistry. After passing Titan, Explorer 1 exited the plane of the solar system, marking the end of its planetary encounters but the beginning of its journey into interstellar space. Explorer 2, following a similar trajectory, reached Jupiter in July 1979 and Saturn in August 1981. Unlike Explorer 1, Explorer 2 continued on to Uranus and Neptune, becoming the first spacecraft to fly by these distant planets. In January 1986, it captured the first close-up images of Uranus and its moons, discovering 10 new moons and observing the planet's unusual sideways rotation. By August 1989, Explorer 2 arrived at Neptune, taking breathtaking pictures of its dark blue atmosphere, supersonic winds, and storm systems, including the Great Dark Spot. The spacecraft also flew by Triton, Neptune's largest moon, revealing geysers of nitrogen gas and signs of cryovolcanism. After their planetary missions, both explorers were directed toward interstellar space. In 1990, NASA announced the commencement of the Explorer interstellar mission, focusing on investigating the outer boundaries of the Sun's influence. Despite their age and the vast distances involved, both spacecraft continued to communicate data from the farthest reaches of the solar system. One of the most iconic moments in the mission occurred on February 14, 1990, when Explorer 1, at Carl Sagan's request, turned its camera back toward Earth, capturing the famous pale blue dot image from 3.7 billion miles away. This photograph, a small in the vastness of space, has since become a powerful symbol of Earth's fragility and humanity's responsibility to protect our planet. On August 25, 2012, Explorer 1 became the first human-made object to enter interstellar space, crossing the heliopause, where the solar wind meets the interstellar medium. Explorer 2 followed suit on November 5, 2018. The data returned by both spacecraft have provided significant insights into the density, temperature, and magnetic fields of the interstellar medium, challenging existing models of the solar system's boundaries. The explorers have made groundbreaking discoveries, including the identification of a new type of plasma that is denser and cooler than the solar wind plasma within the heliosphere. These findings have broadened our understanding of the processes that shape stars and planetary systems. Additionally, the explorers have documented an increase in cosmic rays, demonstrating that the heliosphere acts as a protective shield against these high-energy particles. The spacecraft's data on magnetic fields in interstellar space has prompted scientists to reconsider how these fields interact with cosmic rays and other particles. Theoretical models suggest that the explorers could encounter even more extraordinary phenomena, such as dark matter or dark energy, which remain enigmatic but are believed to make up the majority of the universe's mass and energy. While direct evidence is lacking, such interactions could subtly influence the spacecraft's trajectory, offering new clues in the exploration of these uncharted cosmic forces. There is also a slim possibility that the explorers could uncover evidence of extraterrestrial technology, raising intriguing questions about life beyond Earth. However, the chances are slim, and any such discovery would dramatically alter our understanding of the universe and humanity's place within it. NASA has worked tirelessly to keep the aging Explorer spacecraft operational for over 40 years through innovative engineering, careful power management, and mission oversight. The spacecraft have continued their journeys long after their initial 5-year missions, powered by radioisotope thermoelectric generators, RTGs, that convert heat from decaying plutonium-238 into electricity. As the plutonium decays, the power output gradually diminishes, prompting NASA to strategically shut down non-essential systems to conserve energy and ensure that critical instruments remain active. Communicating with the Explorer spacecraft, now billions of miles from Earth, presents another challenge. NASA employs the Deep Space Network, DSN, a global array of radio antennas, to maintain contact with the spacecraft. As the distance increases, the signals weaken, but NASA has continuously enhanced the DSN's capabilities, enabling ongoing communication and data transmission from these remarkable explorers. The transmission of critical information is essential, particularly regarding the rocket's trajectory, which requires precise control of gyrators. Additionally, the engines are utilized sparingly to regulate power for the scientific instruments still operational, such as those in the Plasma Science experiment and the Vast Beam subsystem, which continue to provide significant data about interstellar space. Despite diminishing power levels, the spacecraft remain functional. However, by the mid-2020s, they may no longer be able to power their instruments, marking the end of their mission. Nevertheless, even after the spacecraft ceases operations, their legacy will endure. The data they have collected has profoundly changed our understanding of the universe and symbolizes the triumph of human curiosity and creativity. Both spacecraft also carry a golden record, a message intended for any extraterrestrial life they may encounter, ensuring that humanity's story will persist for billions of years as they traverse the cosmos. The Explorer mission is undoubtedly one of the most remarkable and enduring achievements in the history of space exploration. What began as a modest plan to study the outer planets of our solar system has evolved into a grand endeavor, providing humanity with invaluable insights into the universe. Originally designed for a short mission, the Explorer spacecraft have exceeded expectations, delivering significant discoveries for over 4 decades and still transmitting vital information back to Earth. These ongoing transmissions hint at new findings that could challenge our current understanding of physics. Recently, after a period of transmitting complex signals, Explorer 1, the most distant human-made object, resumed sending back rational data to Earth. This remarkable achievement underscores the mission's continued relevance and the tantalizing possibility of new discoveries. The Explorer journey commenced in the mid-1970s when NASA recognized a unique planetary alignment that would enable a spacecraft to explore all 4 gas giants, Jupiter, Saturn, Uranus, and Neptune, in a single mission, occurring only once every 176 years. This alignment allowed the spacecraft to utilize each planet's gravitational pull to slingshot toward the next, conserving energy. NASA's Jet Propulsion Laboratory, JPL, developed 2 spacecraft, Explorer 1 and Explorer 2, to capitalize on this opportunity. Launched weeks apart in August and September 1977, these probes were equipped with scientific instruments to study the planetary atmospheres, moons, and magnetic fields. Explorer 1, the faster of the 2, made its closest approach to Jupiter in April 1979, capturing stunning images of the planet's atmosphere and its moons, including the volcanically active Io and the ice-covered Europa. Its findings, such as the presence of active volcanoes on Io and the potential for a subsurface ocean on Europa, transformed our understanding of these celestial bodies. Following this, Explorer 1 proceeded to Saturn, providing humanity with the first detailed images of its intricate ring system and discovering Titan's thick, nitrogen and methane-rich atmosphere. This encounter with Titan altered Explorer 1's trajectory, sending it out of the solar system and initiating its interstellar journey. Meanwhile, Explorer 2 continued on to Uranus and Neptune, revealing new moons, rings, and significant atmospheric details about the two planets. Its flybys, particularly of Neptune's deep blue atmosphere and Triton's cryovolcanic surface, yielded critical data that reshaped planetary science. After their planetary missions, both spacecraft embarked on the Explorer interstellar mission, focusing on the farthest reaches of the Sun's influence. A pivotal moment in this new phase occurred in 1990 when Explorer 1 turned its camera back toward Earth, capturing the famous pale blue dot image from 3.7 billion miles away, a humbling reminder of humanity's smallness in the vast universe. In August 2012, Explorer 1 made history again by crossing the heliopause and entering interstellar space, becoming the first human-made object to do so. Explorer 2 followed suit in November 2018. The data from this new frontier, including the density of plasma in interstellar space and the behavior of cosmic rays, has redefined our understanding of the solar system's boundaries and its interactions with the galaxy. One of the key scientific revelations from the Explorer mission is the discovery of cooler, denser plasma beyond the heliosphere. This finding, enabled by Explorer 1's plasma wave subsystem, provided essential insights into the nature of interstellar space, previously thought to be nearly empty. Instead, this region contains matter from ancient supernovae, which contribute to the composition of the galaxy. The spacecraft also gathered crucial data on cosmic rays, noting a sharp increase in intensity after crossing the heliopause. These findings suggest that the heliosphere acts as a protective barrier for the inner solar system, shielding it from harmful radiation from deep space. This information is vital for future human space exploration, as it sheds light on the risks astronauts may face beyond the solar system. Moreover, Explorer has provided insights into interstellar magnetic fields, which are considerably weaker and more turbulent than those within the heliosphere. These observations have prompted scientists to re-evaluate their models of how magnetic fields interact with cosmic rays and affect their propagation through space. While the known discoveries are fascinating, some researchers speculate that Explorer may encounter even more unusual phenomena as it ventures deeper into space. There is ongoing interest in whether Explorer might detect signs of dark matter, dark energy, or even more exotic forms of matter that defy known physical laws. Although such discoveries remain speculative, they ignite the imagination regarding the unknown forces that could influence Explorer's journey. The possibility that Explorer could stumble upon evidence of extraterrestrial technology, while speculative, continues to intrigue scientists and the public alike. Given the vast distances involved, the chances are slim. However, encountering a signal or artifact from an alien civilization remains a captivating thought. If the spacecraft were to inadvertently discover something surprising, perhaps an anomaly in its trajectory or unexplained interference with its signals, it could lead to profound revelations about the nature of intelligence in the universe. Indeed, the golden records carried by the explorers, containing information about Earth and humanity, serve as a hopeful message for interstellar communication. NASA has managed to keep the Explorer spacecraft operational for over 40 years through remarkable engineering feats, including innovative power management strategies and meticulous mission oversight. Originally designed to last only 5 years, these spacecraft continue to function well beyond their expected lifetimes. A critical factor in their longevity is their power source, radioisotope thermoelectric generators, RTGs, which convert heat from the radioactive decay of plutonium-238 into electricity. However, as the plutonium decays, the power output gradually diminishes. NASA has adapted to this by selectively shutting down non-essential systems to conserve energy. The Explorer mission has not only advanced our understanding of the solar system but also sparked public interest in space exploration. The stunning images and groundbreaking discoveries captured the imagination of millions, leading to a renewed sense of wonder about the universe. educational programs and documentaries have emerged, highlighting the mission's achievements and inspiring future generations to pursue careers in science and engineering. In addition to scientific advancements, the mission has fostered international collaboration in space research. Numerous countries have utilized Explorer data to enhance their own scientific endeavors, contributing to a global understanding of planetary systems. Researchers have analyzed the discoveries from the Explorer missions to study solar wind's interactions with interstellar matter, providing insights into the broader dynamics of our universe. As Explorer continues its journey, scientists remain eager to analyze the data it transmits. Each transmission holds the potential for new discoveries about cosmic phenomena, particularly as researchers focus on the heliopause, the boundary marking the end of the Sun's influence, which offers a unique laboratory for understanding astrophysical processes.